Okay, so in the previous video, we derived the equation of radiative transfer. And so in this video, we're just going to go ahead and solve the equation. So if you remember, we ended up with, we spoke about emission, we spoke about absorption, uh, and basically put the two together, and then we got one big equation which had emission and absorption in it. And now we're going to see, and that equation was in as a differential equation. So now we're going to see how you solve that equation, what are the limiting cases we can identify. So before we do the solution, it's useful to think in terms of the optical depth. It just makes the equations much easier. And optical depth is just a proxy for the absorption coefficient. So the formal definition is this: tau is the optical depth. It's just the integral of the absorption coefficient with distance. Okay, so alpha, the absorption coefficient, has units of 1 over distance. ds has units of distance. So tau basically is a dimensionless quantity. It has no dimensions. It tells you how thick the medium is or how absorptive the medium is. And if you just take the simple absorption only case, which we spoke about, you get this solution for the equation of radiative transfer. It just, the specific intensity is equal to the specific intensity at the beginning of your ray or the medium times exponential of minus the optical depth. Now there are two limiting cases. One is called an optically thin medium. So that's when tau is far, far less than 1. And the way to think about this is tau is an integrated quantity over the entire length of the medium which you're considering. And as a ray is going through that length, tau far, far less than 1 just basically means that a large fraction of the energy makes it out. It is not absorbed in the medium. So you can Taylor expand the exponent here for a small argument, and you basically get I equal to I naught times 1 minus tau. Of course, in the limiting case when tau is 0, I equal to I naught. That's the constancy of specific intensity, which we also spoke about. Okay, so the other extreme case is an optically thick medium. So tau is far, far greater than 1. What that means is as the ray is propagating through the length of the medium, almost all the energy is absorbed by the medium. That's what an optically thick medium is. And so, yeah, if I put a large number here, this exponent goes to 0, which means the specific intensity is 0, nothing comes out of the medium. So the way to think about an optically thin medium is, let's say the atmosphere is an optically thin medium on a clear night to optical light, right? So you can see the stars, it's optically thin, almost nothing is absorbed. If you have a cloudy night, you have an optically thick medium for visible radiation. So you almost see nothing of the stars. I is equal to 0 in the direction of the stars. If you have small patchy clouds or if you have fog, then you have an intermediate scenario where tau is, hovering around a value of 1 for the kind of distances you encounter. So let's say if you're looking at something 10 or 20 meters away, you kind of see it, not exactly. So tau is hovering around 1 in that case. Another way to think of optical depth is that it is just a proxy for distance. So that equation basically tells you that d tau by ds is alpha. ds is a measure of distance. So this is telling you that d tau is also a measure of distance. It's just that ds is in real units, in centimeters or something like that. D tau is in some kind of scaled unit, which makes it dimensionless. And that scaling factor is alpha, right? So this is just basically telling you that you can think of the optical depth as a proxy for distance. So you can have a medium where the ray is propagating, and if it only propagates a certain distance, a small distance, then the total optical depth is small. As the ray keeps propagating in the medium, the optical depth keeps increasing, and you see more and more effects of the medium. So that's kind of the intuition of optical depth. It's quite useful to cast the equation in terms of the optical depth because it just simplifies the interpretation. It also simplifies the algebra. Okay, so let's go to the solution. So here is the equation of radiative transfer equation. So di by d tau. Now I've cast everything in units of optical depth. So you're not going to see alphas here. And you're not going to see the epsilon, the emission coefficient. You're going to see the ratio of epsilon and alpha, which is the source function. So I is the specific intensity of the ray. S is the source function of the medium. Tau is the optical depth. And I've cast this such that you can interpret tau as a distance now. So as as the ray is propagating through the medium, it is as if that distance element is measured in terms of the optical depth here. So this, you can view this as a differential equation in sort of in spatial dimension. Okay, so that's a pretty simple differential equation to solve. So I won't go too much into the solution, but I've left enough steps here so that you could recreate the solution with some basic understanding you have of differential equations from previous courses. So how do we do this? Now, this is not a homogeneous solution. So you need to first get the homogeneous solution. And to get a homogeneous solution, you basically set the source function to 0. And then you get the homogeneous solution. That is just basically the solution you have if there is only absorption, right? So if I set s equal to 0, you only have absorption. You know how to solve that equation. You bring I to the left-hand side, so you get di by I is equal to d tau, and then you integrate both sides, so you get logarithm of I is some constant minus tau. And so you basically, this is the homogeneous case, which is absorption only case. How do you get the full solution? The particular solution in this case, the standard trick for these kind of equations is to multiply both sides by the inverse of the homogeneous solution. So exponential of tau in this case. So you just multiply the entire equation with exponential of tau. I've just brought I to the left-hand side from here. I brought it here. And you'll see why I brought I to this side. It's because, oh, sorry, this epsilon has to be S. I think I missed it in one of these equations. That's the source function S. I'll correct it before I post it online. Yeah, so the nice thing about this is this whole thing can be cast as a simple derivative now. So you can verify using the chain rule that the whole LHS is derivative with respect to tau of I times exponential of tau. And the right-hand side is, of course, the source function times the exponential of tau. And now this looks like a simple differential equation to solve. It's in a very similar form to this one, the homogeneous case, sorry. It's in a very similar form to this one. And so, yeah, I won't go through the intermediate steps because they're quite basic. Here's the solution you get. It's worth looking at the solution and see what the different terms mean. So this is, on the left-hand side is I. So this is what we are solving for. The value of the specific intensity as a function of optical depth. And again, optical depth, you can think of it as a proxy for distance. So as the ray is propagating through the medium, you're trying to get the value of I at different points in the medium, and the different points have different optical depths. From the beginning of the medium to that point, the integrated absorption coefficient is the optical depth. So I of tau is I naught. I naught is the value at the beginning of the medium. That's your boundary condition. This term is entirely from absorption, right? It's a multiplicative term. It acts on I naught. And so this is the absorption only solution here. And this part is the emission only solution. So the absorption only solution, we know we've derived this before. This term makes sense. Let's see what the emission only solution is doing. So notice that the integration is on the primed variable here. So the value of this expression here will not contain tau prime once you have integrated. So it's all a function of only tau. So what is this saying? This is basically saying that the amount of emission from the medium itself you get along the ray depends on where it was emitted. So let's say you're at the end of the medium, you're an observer at the end of the medium, and here is the source, you're the observer at the edge of the medium. If you have emission at the edge of the medium, there's not much medium between you and the emitting particles to create a lot of absorption. So all the emission that comes from the very end of the medium is not going to suffer a lot of absorption. But all of the emission that comes from the beginning of the medium has to travel along the ray all the way to the end. So there is a lot of medium in between to do the absorption. And so that's why what you get here is kind of a weighted sum of the emission from different optical depths or different points in the medium. So d tau, tau prime is basically that variable you're integrating over. So if tau prime is very small, you're basically starting at the beginning of the medium. You're here, you're starting at the beginning. Tau prime is really small. you basically get exponential of minus tau times S. So all the emission that is happening at the beginning of the medium is going to go through, is going to get absorbed in the medium itself. And that's why you get an exponential of minus tau. But if tau prime is is almost equal to tau, you're at the end of the medium, right? That means you're at the end of the medium close to where the ray is exiting the medium. And there, the exponent here, the argument of the exponent will go to 0. Tau prime is almost equal to tau, and you get the entire source function. So you basically see all of the emission that is happening at the edge of the medium. You don't see much of the emission that's happening, at a large distance behind the medium. So that's what this equation basically tells you. It makes intuitive sense. If you develop enough intuition about it, you don't even have to go through these steps. You know that the medium is going to absorb by this law. So the absorption term is easy. And the emission term, you know that you need to have a weighted sum, because emission which is emitted at different points in the medium has to go through different distances in the medium to come to you. And so it will go through a different amount of optical depth and it will get absorbed by a different amount. So this basically is the solution for the equation of radiative transfer. Another thing we can do, sorry, so we can actually go back to the concepts of optical depth which we had and see what the solution looks like in these two regimes. So remember, that is the final solution to the equation of radiative transfer. And so now we can say what the solution looks like in the two limiting cases, the low and the high optical depths. So if you have a low optical depth, which is an optically thin medium, then the first term of the equation, you can Taylor expand the exponent and it just becomes I naught times 1 minus tau. And the second term, you can basically integrate this. So I've assumed here that S does not depend on the optical depth. So it does not depend on where you're in the medium. So it's a homogeneous medium. So once S comes out of the integral, there's just the integral of an exponent. So that's easy. So you can carry out that integration and you get 1 minus exponential of minus tau, which again, if you Taylor expand the exponent here for small tau, you get tau times S. So what does it tell you? It tells you that in an optically thin medium, what you get out is kind of a weighted sum of what you put in and what the medium itself is emitting. What you put in is diminished by 1 minus tau, but the medium basically does not, you don't see the entire source function. Because it's an optically thin medium, you only see a small fraction of the source function added to the specific intensity. And that fraction is given by the optical depth. So you can think of the optical depth as some kind of a clutch between two things. If the optical depth is too high, then you're taking the dial all the way in one direction, where you're seeing more of the source function, which is a property of the medium itself. But if the optical depth is very low, then the dial goes in the other way, and you don't see much of the medium. The medium kind of becomes transparent, and you see more of what is behind the medium, right? So I naught is what is behind the medium. So if you have an optically thick medium, the same intuition again applies. So you start off with the equation, but now tau is far, far greater than 1. So this goes to 0, right? So this is 0. Sorry, this equal to sign should be 0. So it's approximately 0 plus. And this here again, you can take S out of the integral and then you can basically integrate the exponent. It's straightforward. And again, if tau is very high, this again goes to 0 and you just get S. So what does it mean? It means that if you have an optically thick medium, you only see the medium. You only see the emission from the medium. You don't see anything from what is coming from behind the medium. That I naught is completely extinguished. So again, it comes back to this analogy of the optical depth is like a dial, okay? On one end of the dial is what is behind the medium, the specific intensity of the ray which is entering the medium. So what is between you, the medium is between you and some source, let's say, and that source has the specific intensity of I. That's one end of the dial. The other end of the dial is the emission of the medium itself. So if the optical depth is very low, you basically go to one end of the dial, which is you just see the background source. You don't see the emission from the medium itself. But if the optical depth is very high, you go to the other end of the dial where you're only seeing emission from the medium. So a nice example of that, the example at least the one which drove this point home to me, comes from our own Earth, right? So we have a plasma that surrounds the Earth called the ionosphere. The kinetic temperature of the electrons and of the plasma, the electrons and protons in the ionosphere is, I'm doing order of magnitude estimates here, about 1000 Kelvin. Okay, so that's way hotter than the temperatures you and I experience on the Earth. So we experience temperatures of the order of 300 Kelvin. This is significantly hotter than that. But it has a very low optical depth, right? So we can see through the ionosphere in most wavelengths. And that's why you don't feel that 1000 Kelvin heat from the ionosphere, because it is just optically thin. The dial is all the way to one end. And so you just see right through it, and then you look at the stars. You just see the cold space outside and the stars. You don't feel that 1000 Kelvin heat. If the ionosphere were optically thick, then we would be cooking in a radiation of 1000 Kelvin. So that's kind of a nice example of how to think of optical depth. It's a dial basically. And depending on the optical depth, you either see more of the background source, which is behind the medium, or more of the emission from the medium itself. That's a nice way to think about it.